Hi, my name is Ester Andrade. I am a master degree student of Nuclear Engineering Department of Federal University of Minas Gerais and a member of the Monte Carlo Modeling Expert Group. And today I will present our work, Monte Carlo Modeling and Simulation of a new 3D printed phantom for whole body contour calibration. And the whole body contour calibration systems play a fundamental role in non-invasive assessment of internal radioactive contaminants in individuals, estimating the activity in the body at the time of the in vivo monitoring. And the use of biokinetic models and computational simulations allows the estimation of the incorporated activity and the distribution of absorbed doses in various organs and tissues. And the whole body contour systems traditionally utilize various detector materials such as sodium iodine scintillation detector and the high purity germanium to detect gamma radiation emitted by internal radionuclides. To accurately assess absorbed doses in internal dosimetry applications, calibration of in vivo monitoring systems is paramount. Traditionally, calibration procedures are designed in such a way that the count rate measured by the detector of the whole body contour can be correlated with a non-standardized activity of one or more radionuclides incorporated into a anthropomorphic physical phantom. And some examples of physical models include the bottle mannequin absorption, the BOMAP phantom, this one, modulated EMA phantom, this one, and the ego physical phantom. And usually these phantoms have a family phantom of different size, like we can see here in ego phantoms. This is some examples. There are various phantoms for whole body calibration, but in general, their geometrical profiles predominantly comprise cylindrical and ellipsoidal shapes, approximating the cranial, thoracic, abdominal, pelvic, and limbic regions. And anatomically, whole body specific phantoms represent a promising avenue for refining calibration methodologies, enabling a more faithful emulation of human form and minimizing potential measurement discrepancies. The RFPID, that is Reference Female Phantom for Internal Dosimetry, is a new homogeneous anthropomorphic and anthropometric physical phantom, 3D printed, and ongoing, developed by the authors, by our group, and based on the reference computational phantom adult female of ICRP publication 110. So our phantom has 16 compartments 3D printed with PLA filament, and these compartments have an empty cavity inside to be filled with a tissue equivalent material mixed with a non-activity of a certified Europe 152 source. The ballistic gel was the material tissue equivalent planned for this purpose. However, since the filling process is laborious and involves risks of internal and external contamination, it is convenient to know the performance of the physical model built with the proposed materials compared with a heterogeneous human body. So here we have the RFPIT physical phantom model and 3D printed. In first image, we have the physical model, and there is a reference female woman with 160 centimeters of height and 60 kilograms of weight. And in second image, we have a 3D rendered image of the physical model. And third image is the transversal section of the computational model that we developed. So the aim of this work was to use the MCMP 6.2 multicolor code to simulate the homogeneous RFPAT 3D printed physical phantom, fill it with ballistic gel, and compare it to established heterogeneous RCP-AF computational voxel phantom, and exploring the system's performance across a wide range of energies and assessing its suitability for whole bar counter calibration. The computational phantom was based on the images used in the 3D printing process, and these images were joined up to assemble the full model and have matrix dimensions of 178 per 565 per 82 cubic millimeters and a voxel size of 3 per 3 per 3 cubic millimeters. The raw image of the full model was converted to data compatible with the MCNP code using an in-house program in C++. For the computational phantom of our phantom, entailed the utilization of three distinct materials: PLA, serving as the filament for the 3D printing process, ballistic gel, employed as the internal filling material, and external air of the surrounding environment. Due to the lack of data available in literature about the chemical composition of the gelatin used to produce the ballistic gel, a way to simulate it is as a filling material was to consider the composition of the water and the density of the experimentally obtained ballistic gel. That was 1.09 grams per cubic centimeter. And the density of PLA was obtained experimentally too. The computational phantom was positioned in beds of in vivo monitoring system at the center of the development of nuclear technology of National Commission of Nuclear Energy of Brazil. And the system was previously modeled and validated by Pacheco. The system is equipped with sodium iodine scintillator detector, and the source was uniformly distributed into the ballistic gel compartments with monoenergetic isotropic photons. And the Tele F8 card was used to evaluate the photon pulse height on sensitive volume of the detector per photon emitted in the source of the model. And the spectral data was obtained in 1024 energy bands with energy steps for 3 keV, ranging from 3 keV to 3072 keV, which simulates the configuration of sodium iodine detector for the whole bar counter of CGTN laboratories. The absolute efficiency for each energy was calculated as the quotient of the pulses at the photopeak channel per particle emitted at the source. And for purpose of comparison, the same geometry and particle energies of the simulations with RFPAT were conducted with the RCP-RF-AF heterogeneous phantom. But in this case, the radiation source was homogeneously distributed throughout the soft tissues of the phantom. Here we have a sagittal and transversal slice of RFPAT on the left of the image, and the same slices for RCPAF on the right of the image. Here we have a table with the efficient results for RFPAT and RCPAF for different monoenergetic photons. And the relative errors to the simulation results were lower than 1% for all energies, except for 25 keV. For this energy, the relative error was inferior to 1.5%. Among the energies studies, the efficient peak occurred at the energy of 250 keV, and the higher difference is in the 25 keV energy, with a difference of 31% between the both phantoms. The reduced detection efficiency of a sodium iodine for low energies, like the two first, the two lower density, and can be attributed to the high photon absorption in the body and in the window of the detector. Furthermore, discrepancies for this photon energy are not a major source of concern, since sodium iodine detectors have an excessive variation in the detection efficiency in the low energy region. And in the energy ranging from 50 to 1000 keV, the differences were lower than 8%. And this energy region is important for the detection of internal contaminations using this detector, because higher efficiency, low noise, and the fact that several radionuclides of interest emit gammas in this energy range. So the use of correction factors is indicated if it results with a higher degree of accuracy are required. These factors can compensate for the deviations that may arise during whole body control system calibration at these energy levels, and could be an important step to achieving accurate dose estimation. And for energies of 1250 keV to 3000 keV were not statistically significant, since the relative errors were the same order of magnitude. Such consistency in the calibration coefficient simplifies the calculation process for those assessments in this range. This is the efficiency curve as a function of energy obtained from the table data, where we can visualize better. Its aspect aligns with the findings in previous research with the sodium iodine scintillator detector on context of the in vivo monitoring systems. Here we have some examples of this. For example, Pacheco, in his simulation regarding the content efficiency of the scintillator detector employed in this study, also observed similar curve pattern. Likewise, Lebach reported analogous curve characteristics in their simulation work involving the EMA Holy Body phantoms, spanning from pediatric to adult size, and this consistent pattern persisted across all these phantom sizes. And furthermore, Park discerned the same difference curve configuration concerning energy in their experimental setup and stimulation utilizing a male BOMAP phantom. These concordant findings emphasize the consistency of the efficient curve shapes with respect to energy across various studies and methodologies, underscoring its applicability and the relevance in the radiation detection and monitoring. The results demonstrated the RFPIDs printed, 3D printed with PLA and filled with the ballistic gel could be used as a calibration phantom for whole body control systems. Nonetheless, when adequately filled with ballistic gel containing Europe 152, experimental validation with the physical model will be required to confirm the results of this study. And thus, future work aims to incorporate Europe 152 to the ballistic gel to fill the 16 compartments of the physical model and use it for calibration of the in vivo monitoring system of CGTN-CNN in Minas Gerais, Brazil. I'm thankful for the institutions for the financial support of FAPMIG, CAPS, and CNPq, and the Brazilian Nuclear Technology Development Center, where this work was developed. And here is my email address for contact. I appreciate your attention for this presentation. Thank you so much.